Welcome back, Design Junkies. We are Mechanical Engineering Made Simple, Thermodynamics, lesson time 2 of 5. School gave you perfect formulas that always work on paper. The shop floor is waiting to burn your ass in ways those books never even mention.
Oh man, yeah. That is the brutal truth right there.
Right. I mean, think about it. Imagine the scenario. You are standing on the concrete floor of the testing facility.
Just smelling that hot oil.
Exactly. Hot oil, ozone, it's just heavy in the air. And the noise is like a physical weight pressing against your chest. You know, a high-pitched 50,000 RPM whine from the test cell that just vibrates right through your safety boots.
You can feel it in your teeth.
Yeah, you really can. And this is your operation, your test stand. Your career is completely on the line. Behind the blast glass, bolted to this massive rig, is the multi-stage axial air compressor you spent, the last 18 months designing for a next-generation gas turbine.
And let me guess.
Yeah.
The computer models during the design review were just an absolute masterpiece, right?
Yeah. Oh, they were beautiful. I mean, we're talking pristine CFD renders with those perfect smooth color gradients, you know the ones. Transitioning from cool blue at the inlet to a neat fiery red at the discharge.
Gotta love the blue to red gradient.
It's mandatory. And on paper, this machine was precisely calculated to deliver an 8-to-1 pressure ratio with really aggressive efficiency.
But I'm guessing reality has a different plan.
Oh, a completely different plan. Right now, in the unforgiving realm of physical reality, it is failing spectacularly.
Ouch.
Yeah, the red strobes on the control panel are flashing. The dynamometer is showing that the compressor is drawing a massive amount of excess shaft power from the drive motor.
Way over spec.
Way over. And worse, the discharge temperature sensors are completely redlined. The air coming out is dangerously hot, and you are not hitting your pressure targets.
That is a nightmare scenario.
It gets worse. The project manager is standing right behind you, tapping his watch, just waiting for an answer. Your beautiful CAD model is totally useless now. You have to diagnose a bleeding machine right now, using nothing but the raw laws of physics.
Which is, it's the terrifying but also kind of exhilarating moment every real engineer eventually faces.
Right. You're out of the theoretical sandbox.
Exactly. You are no longer designing, you are performing an autopsy on a living machine. And when you're in that high-stress environment, just staring at a wall of angry data, the absolute worst thing you can do is start tweaking variables blindly.
Like just pulling levers and hoping for the best.
Yeah, you don't just start altering blade pitches or opening bleed valves to see what happens. You have to build a diagnostic foundation from the ground up. You have to strip away the complexity of the spinning metal and look at the fundamental flow of energy.
Okay, so let's kick off part 1 of this deep dive. I'm calling this section the steady flow energy equation and stagnation enthalpy in open systems.
Sounds very official.
Well, we need a baseline. Because my first instinct when I see temperatures skyrocketing and power draw going through the roof is to panic.
Sure.
And my second instinct is to assume the technicians just wired the sensors wrong.
Oh, it is the classic engineering defense mechanism. Just blame the instrumentation.
Right.
And look, I mean, sometimes the thermocouple is just fried. It happens.
Right.
But to actually verify what those sensors are screaming at you, you have to anchor yourself to the bedrock of fluid mechanics. You start with the most basic rule of the universe, the continuity of flow.
The cosmic bouncer.
That's a really good way to put it, the cosmic bouncer. If we assume a steady flow, meaning the machine has been running for a few minutes and the conditions aren't fluctuating wildly, the mass of air walking through the front door of your compressor must exactly equal the mass of air exiting the back door.
Because the air isn't vanishing into a black hole.
Right. And it isn't magically multiplying inside the casing either.
So we're talking about mass flow rate, m dot, and the formula for that is m dot equals rho 1 times Cn1 times area 1, which has to equal rho 2 times Cn2 times area 2.
Exactly. So that's the area of the inlet multiplied by the normal velocity of the air, multiplied by the density of the air, rho.
And that total pounds per second number is locked in.
Locked in stone.
So if the air gets squeezed and the density of the rho shoots up, then the area has to shrink or the velocity has to change just to keep that fundamental mass flow constant across the entire machine.
Precisely. You check the inlet mass flow sensors against the exhaust mass flow sensors. If they match, your foundation is solid. The sensors aren't lying to you.
Okay, so the bouncer says the head count is correct.
Yeah, you really are moving the exact amount of air you designed for. But the motor is working vastly harder to do it, and the air is getting vastly hotter than it should. So this forces us to move one level deeper, from the conservation of mass to the conservation of energy. We have to apply the first law of thermodynamics.
Okay, Here is where my textbook and memories start to, betray me a bit. When I think of the first law, I think of a sealed piston compressing a trapped pocket of gas, or maybe a bouncing ball, or a sealed spring mass system. I always think of a closed box.
And that is exactly where a lot of young engineers get tripped up on the floor. A closed system deals with a fixed, trapped mass. You push a piston down, you do work on that trapped gas, the temperature goes up.
Right, and to get it to reset back to the start, you have to extract that heat.
Exactly. But your gas turbine compressor is fundamentally different. It is an open, steady flow control volume. You have a relentless river of fluid continuously crossing the boundary of your system.
So the accounting ledger for the energy has to look different. We aren't just looking at the energy inside a box, we are tracking the energy riding along with the mass as it flows in and out of the doors.
That's it. We use the steady flow energy equation. Functionally, it says that the rate of heat supplied to the system, Q dot, minus the physical shaft work the system's doing, W dot sub x, that difference must perfectly equal the total change in the fluid's energy from entry to exit.
And that total change is multiplied by our mass flow rate, m dot, right?
Yes. So the right side of the equation is m dot multiplied by a big bracket. Inside the bracket, you have the change in specific enthalpy, which is H2 minus H1, plus the change in kinetic energy, which is 1/2 times C2 squared minus C1 squared, plus the change in potential energy, which is G times Z2 minus Z1.
Okay, that is a mouthful of variables. Let's strip away the fluff for our specific nightmare on the test stand. Potential energy, the gravity part with the Z variables, we can throw that right in the trash.
Absolutely.
Because we aren't pumping water up the side of a dam, we are moving air horizontally through a metal tube. Gravity just isn't a factor here.
Correct. The change in elevation is effectively zero, so potential energy vanishes from our equation entirely. Now we are left with enthalpy and kinetic energy. But in turbomachinery, dealing with static enthalpy and velocity as separate variables is just incredibly cumbersome.
It's annoying to track them both.
Very. So engineers use a brilliant shortcut called stagnation enthalpy. We denote it as hay naught.
I love this concept. If static enthalpy is the thermodynamic energy a gas has just sitting there, and kinetic energy is the energy of its physical motion, stagnation enthalpy is what happens if you force the gas to pay the piper.
Oh, I like that. Pay the piper.
Yeah. It is the total energy the fluid would have if you somehow grabbed it while it was flying through the compressor and slammed it into a brick wall, bringing it to a complete adiabatic dead stop.
Bang. Zero velocity.
Right. All that forward velocity, all that kinetic energy gets instantly converted into thermal energy, spiking the temperature and the enthalpy. So 8 naught equals static H plus 1/2 C squared.
It is the absolute maximum thermal energy available in the flow at that exact location. By using stagnation enthalpy, we roll the static properties and the velocity properties into one incredibly useful single number.
That makes the math so much cleaner.
It really does. So now let's look at the other side of the equation, the heat and the work. Our compressor casing is essentially just a thick piece of metal. While it might feel hot to the touch on the outside, the actual amount of heat transferring from the casing into the ambient room air, that Q dot term, is a tiny, negligible fraction compared to the massive megawatts of energy being violently transferred inside by the spinning rotor.
So for all practical diagnostic purposes, it is an adiabatic process. Heat transfer to the room is effectively zero.
Yes, so the Q dot term vanishes.
Right.
And because this is a compressor, the system isn't doing work for us, right? We are actively doing work on it.
We are pumping shaft power from the motor into the fluid.
Exactly. So when you clear away all the zeroed out terms, you are left with an incredibly elegant but brutal truth. The shaft work you are paying for from the electrical grid, W dot sub C, is directly and perfectly equal to the mass flow rate multiplied by the change in stagnation enthalpy from the inlet to the outlet.
So W dot sub C equals M dot times the quantity 8 naught 2 minus 8 naught 1.
That's the one.
Okay, so I am standing on the floor staring at the flashing red temperature alarms. How does this beautiful, elegant equation explain why my project manager is currently yelling at me?
Well, for an ideal gas like the air we are compressing, enthalpy is directly married to temperature. It is literally just the specific heat of the air, C sub P, multiplied by its absolute temperature, T.
So H equals C sub P times T.
Right, so a massive spike in temperature on your discharge sensors fundamentally guarantees a massive spike in your exit enthalpy.
Oh. And if your discharge enthalpy is way higher than your CAD model predicted, our first law equation dictates that your shaft work must also be way higher just to push that exact same mass of air.
Exactly. The motor isn't broken, it is screaming because the fluid dynamics inside the casing are demanding vastly more energy than you anticipated.
Okay, I have to challenge this, or at least try to visualize the physical reality of what you're saying. The first law is the conservation of energy. It is absolute.
Unbreakable.
Energy cannot be created or destroyed. So the motor is dumping megawatts of power into the shaft. The shaft is spinning the blades. The energy is successfully leaving the motor and entering the system. Where is it going? Like,
Hmm.
if I am paying a massive premium in electrical power to get a high pressure ratio, but instead I'm just getting ungodly amounts of heat, is the machine physically broken? Are the massive journal bearings seizing up and generating friction? Is metal grinding against metal?
It's a valid hypothesis. I mean, mechanical losses bearing friction, windage, oil shear, they are real. But here's the reality of heavy turbo machinery. Those mechanical losses usually account for maybe 1 or 2% of the total power.
What's tight?
It is. When you are looking at a thermodynamic deviation large enough to set off alarms and threaten the structural integrity of the casing, it is almost never the bearings.
Because they would have melted.
The bearings would have melted into liquid slide long before the air temperature deviated this much. No, the energy is successfully transferring from the metal into the air. But instead of organizing that energy into a neat, uniform rise in pressure, the system is shredding that energy into chaotic, random thermal motion. The fluid itself is actively fighting you.
Okay, so to figure out why the fluid is rebelling, we can't just treat the compressor like a black box with an inlet and an outlet anymore.
No, the black box model is done.
The first law tells us the energy transfer is inefficient, but it doesn't tell us why. So we have to metaphorically rip the casing off the machine and look at the actual geometry of the spinning metal. We need to look at how a blade actually imparts force to a gas. Which brings us to part 2. Euler's pump equation and Rothalpy in turbomachine rotors.
Let's do it. We need to leave pure thermodynamics for a moment and step into kinematics. We need Newton's second law applied to rotating fluids, the momentum equation.
Right, because a jet engine compressor isn't just a giant ceiling fan.
Far from it. In a linear system, force equals mass times acceleration. Simple. But in turbomachinery, everything is spinning around a central axis. So we use the law of momentum.
And what does that say?
It dictates that the total torque applied by the shaft to the rotor is equal to the mass flow rate of the fluid multiplied by the change in its angular momentum.
Let's ground this for the listener who is trying to picture the inside of this screaming machine right now. You have the central shaft. Attached to that shaft is a heavy metal disc. Protruding from that disc are dozens of incredibly complex, aerodynamically shaped titanium blades.
Yep, the rotor array.
The air enters the front of the spinning row of blades at a certain radius, and it leaves the back of the row.
And as it passes through, the blades physically slap the air, altering its trajectory. This brings us to Euler's pump equation, which is arguably the single most important mathematical relationship in all of rotating machinery design.
It's the holy grail of turbomachinery.
It really is. Euler proved mathematically that the specific work done on the fluid by the blades is purely a function of blade speed and fluid swirl.
The equation is delta W sub c equals U2 times c theta 2 minus U1 times c theta 1. I want to spend some time right here because this equation is an absolute mind bender when you truly understand what it implies.
It completely changes how you view a spinning blade. Let's define the players.
Right, so U is the physical literal speed of the metal blade itself. It is the rotational speed of the shaft, omega, multiplied by the radius, r. So the tip of the blade is physically traveling through space much faster than the root of the blade near the hub.
Correct. And the c theta term is the tangential velocity of the fluid. It is the component of the air's speed that is swirling in a circle in the exact same direction the blades are spinning.
And this is the aha moment. Euler's equation mathematically proves that a spinning blade does not do work by just pushing the air forward like a snowplow.
Not at all.
The only way a spinning rotor can impart energy to a fluid is by changing its tangential momentum. You have to change its swirl. If the air enters the blade row swirling at, say, 100 miles per hour, and it leaves the trailing edge of the blade still swirling at 100 miles per hour, you have done zero thermodynamic work on that fluid, no matter how fast your shaft is spinning or how much noise the machine is making.
It's a profound realization.
Right.
You're essentially using an aerodynamic pressure differential, the difference between the high-pressure face and the low-pressure suction side of the curved blade, to forcefully bend the air's path, inducing a massive swirling vortex. The work you put into the shaft is fundamentally the effort required to create that swirl.
Wow.
Now, if we take this purely mechanical reality Euler's swirl equation
Yeah.
and we smash it together with our thermodynamic reality, the first law enthalpy equation, something incredible happens.
This is where we uncover Rothelbachby, right?
Yes. We establish that the work done equals the change in stagnation enthalpy. And Euler tells us that same work equals the change in the product of blade speed and swirl. If we set those two equations equal to each other, and we put all the inlet conditions on the left side of the equal sign and all the outlet conditions on the right side.
We discover a new invariant property.
Exactly. We find that static enthalpy H plus kinetic energy, 1/2 c squared, minus the products of blade speed and swirl, U times c theta, equals a constant value throughout the entire rotating blade passage.
It is a constant. We call it Rothelbachby, which stands for rotational stagnation enthalpy. The letter I equals H plus 1/2 c squared minus U times c theta.
Yes.
I want to try an analogy here because grasping Rothelbachby is like seeing the matrix for fluid dynamics.
Okay, let's hear it.
I imagine an air molecule entering the compressor is like a gambler walking into a very high-stakes rotating casino.
We're rotating casino. Okay, let's see where this goes.
You walk in with 3 types of currency. You have static enthalpy, which is your poker chips. You have kinetic energy, which is the physical cash in your wallet. And you have a line of credit based on how fast the floor is spinning and how much you are swirling. That is the U times c theta term.
Okay, follow.
As you walk through the casino, or as the air molecule moves along the flow path between the blades, you can trade your assets back and forth at the tables. The shape of the blade passage acts like a dealer. It might force the air to slow down relative to the blade, converting kinetic cash into static enthalpy chips, raising the pressure.
Right, diffusion.
Or, as the radius changes, it might alter your swirl line of credit. You can shift the wealth around into whatever thermodynamic form you want, but the house rules are absolute. The total net worth of your portfolio, your Rothelbachby, is locked in stone from the microsecond you hit the leading edge of the blade until the moment you slip off the trailing edge. The ledger must balance perfectly.
That is actually a highly effective way to visualize a complex Eulerian frame of reference. Because the casino is moving with the blades, from the perspective of an observer riding on the blade itself, the total energy of the flow is rigorously conserved. Rothelbachby remains completely unchanged along the flow streamlines.
It's the ultimate accounting trick.
It really is. It is the bridge that links the physical shape of the blade to the thermodynamic state of the gas.
So, armed with this knowledge, we turn back to our failing test stand. The machine is screaming. We decide to verify the hardware. We shut it down, we pull the massive steel casing off, and we laser scan the titanium rotor. We check the blueprints. The blade angles are machined to perfection. They possess the exact curvature required to induce the precise amount of swirl, c theta, that Euler's equations demand. We verify the dynamometer. The motor's holding the exact RPM, so the blade speed, U, is dead accurate.
So the physical kinematics are flawless. The rotor's doing exactly what it was geometrically told to do.
Exactly. The first law is intact. Energy is not mysteriously vanishing. The mechanics are verified. The blades are inducing the correct momentum change. The Rothelbachby ledger balances perfectly. So if the machine is physically perfect and the energy is accounted for, why am I still failing to hit an 8-to-1 pressure ratio?
It doesn't seem to make sense.
Why is all my expensive shaft power turning into raw, useless heat instead of beautifully organized pressure?
Because up until this exact moment in our diagnostic journey, we have made a fatal assumption.
Which is?
We have only looked at the quantity of energy and the mechanics of momentum. We have completely ignored the physical quality of that energy. Our equations so far have assumed a perfect, frictionless reality.
Ah, the ideal world.
Exactly. To solve this crisis, we have to look into the dark heart of physics. We must confront the second law of thermodynamics. Which brings us to polytropic efficiency versus isentropic efficiency in multi-stage compressors.
This is where the Timms book betrays the young engineer.
Brutally. The second law introduces the concept of entropy and an ironclad rule known as the inequality of Clausius.
The cyclic integral of dq over t is less than or equal to 0.
Right. And without getting bogged down in 19th century cyclic integrals for our open, steady flow compressor, the second law dictates a very simple truth regarding entropy generation.
Okay, lay it on me.
The rate at which entropy is generated inside that casing must always be greater than or equal to 0. S dot sub gen equals m dot. multiplied by the difference between S2 and S1, and that whole thing is greater than or equal to 0.
And the equal to zero part is a complete fairy tale, right? That only exists in a perfectly reversible, frictionless universe where air molecules never bump into each other the wrong way.
Right. In our physical compressor on the test stand, entropy generation is strictly, unavoidably greater than 0. And this isn't just an abstract mathematical concept. Entropy generation has physical mechanisms. Well, every single time the air scrapes along the rough surface of the stationary casing, fluid friction generates heat. Every time the high-velocity air tumbles over the blunt trailing edge of a titanium blade and separates into a chaotic, swirling wake, turbulent mixing generates heat. Every microshockwave near the blade tips generates heat.
So all of these microscopic aerodynamic imperfections, which are literally impossible to eliminate entirely in the real world, are constantly bleeding useful mechanical energy into disorganized thermal energy.
Yes, and this brings us to the root cause of your test stand failure. It comes down to how you, the engineer, defined your efficiency targets during the design phase.
Oh no, it's my fault.
It usually is. It is highly likely that when you designed this massive multi-stage machine to hit an 8-to-1 pressure ratio, you assumed an overall isentropic efficiency across the entire unit. Let's say you assumed the whole block could operate at 85% efficiency.
Which seems entirely reasonable. I mean, if I want a machine that is 85% efficient, I'd design the blades to be 85% efficient.
Right. It seems logical, but it is a catastrophic trap. It completely ignores the compounding parasitic nature of entropy. To understand why your machine is failing, we have to split your massive compressor into its individual stages, and we have to introduce a concept called polytropic efficiency, sometimes called small stage efficiency. Let's call it eta sub p.
Okay, let's unpack this carefully, because this is the exact moment the light bulb goes off for anyone trying to troubleshoot multi-stage turbomachinery. What is the hidden thermodynamic effect that is currently destroying my test stand?
Imagine your compressor has 8 distinct rows of spinning blades, 8 stages. As the fresh, cool room air enters stage 1, it gets compressed. But because of the friction and weight turbulence we just discussed, the air leaving stage 1 is slightly hotter than it theoretically should be.
Because the entropy generation has manifested as excess thermal energy.
Exactly.
Okay, so the air is a little warmer than ideal, so what? I mean, who cares about a few degrees?
Because the gas is hotter, its density decreases. Its specific volume, the physical amount of space 1 kilogram of that air takes up, expands. Now this physically hotter, fluffier air enters stage 2. Stage 2 now has to sweep a larger physical volume of gas just to push the exact same mass flow rate.
Oh my God. Because the mass flow rate is constant, our cosmic bouncer from step 1, but the volume has increased, the physical velocity of the air entering the next row of blades has to increase to shove it all through the same annular area.
Precisely. And because the air is moving faster and is less dense, stage 2 had to do significantly more physical work to compress that exact same mass of gas to the next required pressure increment. The blades literally have to fight harder.
Wow.
And because they fight harder, they generate even more friction and even more heat, feeding a devastating feedback loop.
It is exactly like compound interest, but instead of making you rich, it is violently working against you. Let me try a real-world analogy. It's like running a multi-stage relay race up a mountain. The first runner does their leg, but they are slightly inefficient, so they get tired and sweat, which in this analogy means they add 5 pounds of rocks to the team's shared backpack.
Okay.
The second runner takes the baton, but now they have to run their leg carrying an artificially heavier backpack, so they get even more exhausted, and they add 10 pounds of rocks. By the time the baton reaches the stage 5 runner, they are sprinting up a mountain while carrying a boulder.
That is an exceptional analogy.
The later stages in the compressor are working fundamentally harder and failing to hit their pressure targets simply because they are being forced to swallow the thermal garbage generated by the earlier stages.
Yes. The later stages are profoundly penalized for the aerodynamic sins of the early stages. The errors compound geometrically. This is the hidden thermodynamic effect. It proves mathematically that for any compression process, your overall isentropic efficiency, eta sub c, will always inevitably be lower than the aerodynamic efficiency of your individual stages, eta sub p.
Let's look at the math that proves this, because looking at the equation is like looking at a horror movie monster hiding in the shadows.
It's a scary equation for a designer.
The equation for overall efficiency, eta sub c, equals a big fraction. The numerator calculates the ideal work based on your total pressure ratio. It is the quantity P2 over P1 raised to the power of gamma minus 1 over gamma minus 1.
Right, that's the ideal.
But the denominator, which calculates the actual work.
The denominator contains the pressure ratio, P2 over P1, raised to a slightly different exponent. It is raised to the power of gamma minus 1 divided by the product of eta sub p and gamma, and then minus 1.
Buried deep inside that exponent in the denominator is your polytropic efficiency, your small stage efficiency, eta sub p. It is actively scaling the required work based on the stage-by-stage reality.
Let's use the actual example from our source material to put hard numbers to this nightmare. We have an axial compressor designed for an 8-to-1 total pressure ratio. The air comes in at a comfortable 300 Kelvin, but the discharge temperature sensors on the test stand are reading a scorching 586.4 Kelvin.
If you take those numbers and isolate the efficiency of the individual blade rows, the polytropic efficiency, you will find that the stages themselves are actually operating at a very respectable 88.65%.
Your aerodynamic design was actually quite good. The blades are performing beautifully on a micro level.
But because of the compounding heat penalty, the overall isentropic efficiency of the entire machine mathematically drops to roughly 85%. I lost over 3% of my total machine efficiency, not because my blades were bad, but simply because I stacked them in a row and let the heat accumulate.
Exactly. And this reveals a massive pitfall in engineering analysis. It means that comparing the overall isentropic efficiency of two machines with different pressure ratios is a completely invalid, mathematically illiterate procedure.
Because the baseline is completely different.
Right. If you have a small 4-to-1 compressor and a massive 8-to-1 compressor, and both machines possess the exact same blade aerodynamics, the exact same 88.65% stage efficiency, the 8-to-1 compressor will appear to be a significantly worse machine on paper if you only look at its overall efficiency.
Because the 8-to-1 machine has more stages, meaning it suffers from a much larger compounding heat penalty, it is being unfairly judged by the hidden thermodynamic effect.
Yes. The universe forces the later stages to pay the entropy tax of the early stages.
So we finally solved the test stand crisis. I miscalculated the power requirement because I used a flat 85% overall efficiency assumption. I completely failed to account for the fact that the downstream stages would require geometrically more shaft power to compress the artificially heated air.
You didn't account for the rocks in the backpack.
Exactly. My motor wasn't sized to handle the compound interest of entropy. I have to redesign the later stages, or I have to buy a bigger motor. But the pain doesn't stop at the compressor, does it? The machine is just one part of the ecosystem. What happens when this mangled, overheated air leaves the compressor and enters the rest of the turbine?
The consequences ripple outwards, and this requires us to shift our perspective from the machine to the universe itself. We have to talk about thermodynamic availability, exergy, and the quality of energy in turbines. We need to look at the ultimate cosmic tax on your energy.
The first law told us that the quantity of energy is perfectly conserved. The megawatt of power the motor pulled from the grid is still physically present in the hot, swirling air leaving the compressor. But availability tells us that the usefulness, the actual value of that energy, has been fundamentally shattered.
Correct. Energy has quality, not just quantity. Let's follow that hot pressurized gas. It leaves the compressor, goes through a combustion chamber where fuel is added, and then it slams into the turbine section. The turbine's job is to extract work from that hot gas by expanding it back down to atmospheric pressure.
Let's use the source text's specific gas turbine example. The turbine receives this incredibly energetic gas at 10 bar of pressure and 1,000 degrees Celsius.
That's a lot of potential.
It expands it down to the ambient atmospheric pressure of 1 bar. The room we are standing in is sitting at 20 degrees Celsius. The turbine itself has an isentropic efficiency of 85%.
When you perform an exergy analysis on this expansion process, you aren't just calculating how much shaft power the turbine produces, you are calculating the change in availability of the entire universe.
The equation is the change in availability of the universe equals the change in availability of your system plus the change in the surroundings.
And for this specific real-world turbine example, the result is negative 24.0 kilojoules per kilogram.
Negative 24. What does that negative number physically mean to me as an engineer?
It is the ultimate grim reality of the second law. That negative 24 kilojoules per kilogram represents energy that has been permanently, irrevocably degraded. The quality of the energy in the universe has been destroyed.
It's just gone.
It is gone forever. Let me be very specific about what this means. Even if you took the hot exhaust gas, leaving that turbine, and you somehow fed it into a magically perfect, completely frictionless, mathematically reversible heat engine that doesn't exist in reality, it would still be physically impossible to produce as much work as it originally took to compress the gas in the first place.
Let me try a different metaphor here, because the standard textbook analogies never quite capture the tragedy of this.
Go for it.
Imagine you have a perfectly still glass of pure water. That represents the ambient environment. Now, you take a single drop of highly concentrated dark blue ink and you carefully suspend it right in the center of the water. That drop of ink is your highly pressurized, high-temperature gas entering the turbine. It is organized, it is concentrated, it has extremely high availability.
I like where this is going.
As the gas expands through the turbine as time moves forward, the ink drop begins to disperse. It swirls, it mixes with the water turns a cloudy light blue. Now, the first law of thermodynamics guarantees that every single molecule of blue ink is still inside that glass. The total quantity of ink is perfectly conserved.
But the second law, the concept of exergy, dictates that the usefulness of that ink is destroyed.
Exactly. You can never, ever reach into that cloudy water and spontaneously pull out a perfectly organized single drop of dark blue ink. The only way to separate the ink from the water is to hook up an incredibly complex filtration system and pump massive amounts of external electrical work into it.
That is a phenomenal representation of irreversibility. Viscous dissipation, shock waves, turbulent mixing, these are the physical mechanisms that scatter the ink. Work is organized energy. It is all the molecules marching uniformly in one direction to push a turbine blade. Heat is disorganized energy. It is molecules vibrating randomly and chaotically in every direction. The universe naturally degrades organized work into chaotic heat.
And the currency the universe demands for every process is entropy.
And you pay that tax directly out of your availability.
Man, so we have completed the diagnostic journey. We traced the failure of our test stand from the broad strokes of the first law down to the aerodynamic geometry of the blades using Euler, through the compounding nightmare of the second law's polytropic efficiency, and finally faced the cosmic reality of exergy. Having survived that, it is time to pivot.
Time for the lightning round.
Yeah, we are going to take these hard-won principles and answer the most pressing, confusing questions engineers actually have in the field when trying to apply this material. We're calling this section Common Mechanical Engineering Questions on Turbomachinery and Thermodynamics.
Let's do it. No theoretical fluff, just the physical realities.
Okay, here's the scenario. The test stand is shut down. The project manager comes out of his office. He is looking at the performance reports for the downstream turbine section of our engine. He points at the spreadsheet and says, "Why are you evaluating this turbine using total-to-total efficiency? If you just use static efficiency, the numbers look better to the client."
Classic manager.
Right. You have to explain to him why he is fundamentally misunderstanding the physics of the machine.
It is a very common argument. The answer depends entirely on what happens to the fluid after it leaves the machine. Is the exit kinetic energy useful, or is it garbage?
Let's break down the jet engine scenario first.
If you are evaluating the final turbine stage of an aircraft jet engine, the gas leaving those blades is moving at extreme velocities. That kinetic energy is not waste. It is the very thing that provides the propulsive thrust out the back of the nozzle to keep the aircraft in the sky. Because that dynamic velocity is highly useful, you must evaluate the machine using total-to-total efficiency. This metric explicitly accounts for both the static pressure and the dynamic kinetic energy by using stagnation properties.
What if it isn't the final stage? What if it's stage one of a 5-stage turbine?
The exact same logic applies. The high-velocity air exiting stage 1 slams directly into the inlet of stage 2. The kinetic energy is preserved and utilized by the next row of blades. Again, total-to-total efficiency is the only honest thermodynamic metric.
But the project manager argues that he used to work in industrial HVAC, and they always use static efficiency for their big blowers.
And in that specific context, he was entirely right. If you have a massive industrial fan just blowing air into a gigantic cavernous warehouse, the high-velocity air exiting the fan duct just dumps into the stagnant room. That kinetic energy immediately dissipates into chaotic swirling eddies and eventually heat. It does zero useful work. It is entirely wasted.
Ah, I see.
For that machine, evaluating it with total to static efficiency is mandatory. It mathematically penalizes the machine for failing to convert that dynamic velocity back into useful static pressure before throwing it away.
So you use total to total when the exhaust velocity has a jibe to do, and total to static when the exhaust velocity is just being dumped into the trash.
Brilliant.
Oh, okay. Okay, next scenario. A junior tech on the floor is trying to be helpful. He sees that the compressor is drawing too much power, so he suggests, hey, why don't we just install a throttling valve upstream of the inlet? We can drop the pressure of the incoming air, which means the compressor will have to do less work.
Oh, wow.
Yeah. What is the thermodynamic difference between a throttling valve and a turbine, given they both technically drop pressure?
Oh, that is a dangerous suggestion from the tech. Physically, yes, they both induce a pressure drop, but thermodynamically, they are entirely different species of physics. Let's look at the throttling valve first. A throttle is essentially just an insulated pipe with a severe restriction in it, like a partially closed valve or a porous plug.
No moving parts, no spinning shafts.
Exactly.
Yeah.
Because there is no shaft to extract work, the first law dictates that the specific enthalpy remains perfectly constant across the valve. Enthalpy in equals enthalpy out, H1 equals H2. However, as the gas violently squeezes through that tiny restriction, fluid friction is immense. The pressure drops violently. The second law dictates that this highly irreversible process creates massive entropy generation. S dot subgen is way greater than zero.
So the throttle drops the pressure, but it extracts absolutely zero useful work from that drop. It just shreds the availability of the fluid into pure entropy.
Correct. Now look at a turbine. A turbine is actively equipped with a spinning rotor. It forces the expanding gas to push against angled blades. The first law states that the enthalpy of the gas drops significantly from inlet to outlet because that energy is physically leaving the fluid system and traveling down the spinning shaft as extractable mechanical work. W dot sub T equals M dot times the difference between H1 and H2.
So one device, the throttle, wastes the pressure drop entirely to internal friction, doing nothing but generating entropy. The other device, the turbine, actively harvests that pressure drop, converting it into usable shaft power and minimizing entropy generation. Replacing a turbine with a throttle is basically thermodynamic vandalism.
Precisely. A throttle destroys exergy. A turbine harnesses it.
Excellent. Final question from the floor. This one is a bit more theoretical, but it trips up people trying to design closed-loop cooling systems for the test cell. A tech asks, it is 120 degrees in this test cell right now. Can we just build a closed system engine that absorbs the ambient heat from the room, uses it to expand a gas, turns a shaft to generate electricity, and powers our laptops?
And the ghost of Lord Kelvin appears to tell them absolutely not. This is a direct violation of the Kelvin-Planck statement of the second law.
I thought I could just absorb heat and turn it into work.
You can, for exactly one stroke of a piston. A closed system can absolutely sit in a hot room, absorb thermal energy, expand, and push a load. But a true engine must operate in a continuous cycle. It has to reset itself to its original state to take another stroke. The Kelvin-Planck statement dictates that a closed system cannot deliver continuous network while communicating with only one thermal reservoir.
It needs somewhere to dump the thermal garbage so it can reset the piston.
Yes. It needs a hot source to provide the high-quality thermal energy, and it absolutely requires a cold sink to reject the lower-quality waste heat. This creates a temperature gradient, and it is that gradient, that flow of heat from hot to cold, that physically drives the cycle. Without a cold sink, the piston expands once, equalizes pressure, and stops forever.
And the only way to force it back.
The only way to force it to cycle while touching only one reservoir is if you plug it into the wall and use an electric motor to forcefully compress it again, which obviously defeats the entire purpose of an engine.
So essentially, to synthesize this entire exhausting diagnostic journey, every single piece of hardware on that shop floor, every throttling valve, every turbine stage, every spinning compressor rotor is just a different physical manifestation of humanity trying to control enthalpy while desperately fighting a losing war to minimize entropy.
That is the whole job.
That is the entire brutal job of a mechanical engineer. You are fighting the universe's inherent desire for chaos, trying to extract or input useful organized work before fluid friction and turbulence scatter it all into the void.
That is a deeply accurate summary of the profession. We are managers of energy and fighters of entropy, and we usually lose a little bit in every transaction.
I love it. Okay, that brings us to the end of our crisis on the test stand. We verified the mass flow, we tracked the enthalpy spike, we proved the blades were kinematically sound with Euler, we uncovered the compounding nightmare of polytropic efficiency, and we faced the reality of exergy. But I want to leave you with a new thread to pull.
Something to keep them up at night.
A thought experiment to keep you awake during your next shift. We spent this entire deep dive assuming our working fluid air behaved like a relatively predictable ideal gas. We assumed density scales somewhat linearly with pressure, and specific heats remain relatively stable. But what happens to all these beautiful, elegant equations, the Eulerian kinematics, the polytropic models, when your compressor is tasked with ingesting a supercritical fluid?
No, that changes everything.
What happens if you are designing an advanced power cycle and you push carbon dioxide past its critical point at 73 atmospheres? The phase boundary between liquid and gas completely vanishes. Your density behaves erratically, and your specific heats wildly decouple from temperature. The math we relied on today is incredibly powerful, but it is just the shallow end of the thermodynamic pool.
Yeah, when you cross into supercritical regimes, the assumptions of ideal gas behavior utterly shatter. The thermodynamics become vastly more complex, incredibly nonlinear, and extremely dangerous to your hardware if misunderstood.
I will leave you with this. The real lesson doesn't start until your first design fails in ways the textbook said was impossible. If this helped you even a little, please tell us. We're putting this out for free, no paywall, no subscription, nothing locked behind a card. That only works if we know it's actually reaching people and doing what it's supposed to do. If you're a young engineer trying to figure this stuff out and this gave you clarity you weren't getting anywhere else, drop a like, leave a comment. It takes 2 seconds on your end, but it tells us this is worth continuing instead of just talking into the void. We are excited for your feedback, negative or positive.